In today's video, we will be taking a look at the rocks around the UConn campus. As UConn students ourselves, we see rocks around campus all the time, and we have always wondered how they got there. In this video, we answer this question along with others. After watching, you should be able to discuss the features, processes, and relative plate motions associated with convergent plate boundaries, be able to list and identify the rocks and minerals present within the bedrock in the UConn area, and be able to explain how geologists date bedrock and recall the processes to date them. By understanding these ideas, students will have a much better understanding of the local history surrounding UConn. Two important themes we will be covering are exposed bedrock, which can be defined as hard, consolidated, solid rock that is tightly bound and exposed above the surface, and metamorphism, which can be defined as the solid-state transformation of pre-existing rock into texturally or mineralogically distinct new rocks as a result of high temperature, high pressure, differential stress, or fluids. About 200 to 300 million years ago, all 7 continents existed together in a megacontinent named Pangaea. Over time, the continents eventually separated and became their own continents, like we see today because of plate tectonic activity. Although there are different types of plate boundaries, the formation of the UConn bedrock occurred in a convergent plate boundary. These boundaries occur where 2 plates move towards each other. This boundary creates important features like trenches, volcanic arcs, and mountain ranges. Some of Earth's largest earthquakes and most devastating volcanoes occur at these convergent boundaries. There are 3 different types of convergent boundaries: oceanic-oceanic, oceanic-continental, and continental-continental. In all these types, subduction occurs, which we will touch on in the next slide. In oceanic-oceanic boundaries, 2 oceanic plates collide with each other, and the denser oceanic crust subducts beneath the other, causing the formation of volcanic island arcs and trenches. In continental-continental collisions, 2 continental plates collide with each other, and again, the denser oceanic crust subducts, causing mountain ranges to form. Finally, in oceanic-continental boundaries, an oceanic plate collides with a continental plate, causing a denser oceanic crust to subduct, which forms continental volcanic arcs and trenches. Subduction occurs because the older oceanic lithosphere is cold and dense. When it moves away from the mid-ocean ridge, the mantolithosphere beneath it thickens. The thicker this mantolithosphere becomes, the easier it is for the oceanic lithosphere to subduct. As it ages, the oceanic lithosphere becomes denser than the asthenosphere, allowing it to subduct. The ballast effect can be defined as using a dense material to provide stability to something. For example, think about a cargo ship. When it's empty, it floats high in the water. When you add a heavy ballast or a weight to the bottom, the ship sinks deeper in the water. Connecting this back to plate activity, when oceanic crust forms at a mid-ocean ridge, it starts out hot and thin. As it moves away from the ridge, it cools down. The cool rock becomes denser, so the lithosphere underneath it thickens as it cools. The more weight, the deeper it sits. The demonstration starts with a glass filled with water with 2 equally sized bottle caps. At first, they are both floating at the same level. For the experiment, we added some water to one of the caps to witness what would happen to it. As you increase the weight of one of the caps by adding more water to it, it sank deeper in the water. This explains the ballast effect because as you added water to the cap, it sank deeper due to the water because of its increased weight. Now that we understand the processes that allowed the bedrock to form, we can start learning about how old the rocks are. Geologists use a process called radiometric dating to determine the absolute age of rocks. This technique measures the decay of radioactive elements and minerals. This is essential for understanding Earth's 4.6 billion year history. Radiometric dating is a method that uses the decay of radioactive isotopes, which are called parent atoms, into stable daughter isotopes. Radioactive decay happens at a constant, predictable rate. By measuring the ratio of parent to daughter isotopes, we can calculate how much time has passed. It works almost like an hourglass, but instead of sand, it's atoms. In order to calculate the age for a rock, geologists must collect a rock sample that is either igneous or metamorphic. Then, they must extract minerals from the rock, specifically looking for minerals that contain radioactive isotopes. Next, you have to measure isotope ratios, which can be done by counting the number of parent versus daughter atoms. This can be done by using sophisticated instruments like mass spectrometers. Using this data, You then calculate the age, which uses the half-life and the measured ratio. The formula for this is half-life times the base 2 log of 1 plus the number of daughter isotopes divided by the number of parent isotopes. You may be wondering what is actually beneath our feet at UConn and what specific rocks are below us. Connecticut sits on ancient metamorphosed rock, and these rocks tell the story of the mountain building which occurred hundreds of millions of years ago. UConn sits in the eastern highlands of Connecticut, which is part of the ancient Appalachian mountain belt. The Yukon bedrock formed during the Paleozoic era, which was around 540 to 250 million years ago. Around 500 million years ago, during the Ordovician era, sediments like mud and sand were deposited into the ancient ocean. Moving forward to 400 to 360 million years ago, during the Devonian and Akkadian orogeny, continental collision transformed sediments into metamorphic rocks like schist and gneiss. Adding on, the East Coast mountain reached heights similar to the Himalayas. 200 million years ago, during the Jurassic period, Pangaea broke apart and the Connecticut River Valley formed as a rift. During the present time, erosion has worn down mountains, leaving only the metamorphic roots beneath UConn. Beneath UConn, there are two main rock types, schist and gneiss. Schist is sparkly and has layered metamorphic rock, while gneiss is a banded metamorphic rock. Schist can be found in some notable places like the Bolton Schist or the Urban Formation. Also present in the area is granite, which has light-colored igneous intrusions, and quartz veins, which are mineral deposits of quartz within a rock. In order to tell the difference between schist and gneiss, there are many distinct characteristics of both. Schist is medium-grained, while gneiss is coarse-grained. Schist has foliation and it splits easily, while gneiss has banding of light and dark layers. Schist has a sparkly look due to mica, and its main colors are gray, silver, and green. Gneiss has a striped appearance with its main colors of white, pink, and black layers. The best places to find bedrock around the Yukon area are the historic stone walls around campus, the road cuts along Route 195 and Storrs Road, and the Fenton River along with campus stream beds. After researching how the bedrock beneath Yukon is formed, identifying the rocks and minerals that make it up, and learning how geologists figure out their ages, we came to recognize the importance of the history beneath our feet. The bedrock is more than just an old rock. It explains how the landscape changed over time through the process of plate activity, mountain building, and environmental changes. By understanding this history, we can analyze and predict what will happen in the future, making us more prepared for what awaits.